In the next section, we want to look at the Lempel-Ziv compression family, and specifically Lempel-Ziv Welch algorithm as one example of that family, which will be the first algorithm that gives you real sensible compression of this type of repetitive texts in lots of practical examples. Run length encoding was all fine, and we'll use part of that as a building block, but by itself, it doesn't compress most data super well. To warm up, without explaining much how Lempel-Ziv works, I want to just show you this, and there's a Slido question for that, which asks you to produce the second to last line. So this, I'm interested in this line. That's what you're supposed to answer on Slido. A little bit of advertisement at this point. I took this example out of the Computer Science Unplugged collection. These are fun exercises that teach computing concepts without really using computers much. And this is, I think, a really nice example. It doesn't need words to really explain what's happening, but it conveys the idea of Lempel-Ziv so beautifully. And in case you didn't know what peas porridge is, I was told that's the right thing. It's some kind of soup. I don't know. I didn't get a chance to try the original one, but I don't want to try the version advertised in this poem for sure. Okay, so results are trickling in. I think people start to get it. So that's still big enough. All right, I mean, you can type it in, and apart from plus minus commas and stuff, I think people get this. The idea here, of course, is some of these boxes are empty, but instead they are a reference to something that occurs earlier. So you just copy whatever is there. And so you get peas porridge hot, peas porridge cold, peas porridge in the pot, 9 days old, yummy. Some like it hot, some like it cold, some like it in the pot, 9 days old. And you see, not a lot of explicit letters are needed because this is a super repetitive poem. This is pretty much what Lempel-Ziv also tries. It's a more structured and more systematic way of doing that, encoding a text by repeating something that you've already encoded earlier. Of course, if you're doing this with a computer, you have to somehow say what these boxes look like and what do the arrows correspond to. And you want to be frugal with the number of bits you use in both cases. And that's where all the complications start. All right. So far we've mostly focused on single characters, and now we'll definitely go away from that. Again, to motivate this a bit, in many cases you have certain substrings, not just individual characters, that are more frequent than others. There are English words that are much more frequent than other combinations of letters. I mean, THE is probably much more common than XXY, right? And you have the same in other applications. I mean, most of the web is basically a big text file, and a lot of that is some form of XML, which is really not the shortest way to write things. But compression of the Lempel-Ziv type means you don't have to worry about that redundancy too much. It's a whole family of compression methods. They're all adaptive in our classification from earlier, so they don't use a fixed code, but they keep changing the code as they go, which is what makes them quite interesting. In this case, we'll have code words. That's, again, the things that make up the coded text. But in the source text, they can either be a single character or a whole substring. And we'll have to make sure that the encoder and decoder stay in sync about what that means. There's lots of variations of that idea in different ways. What exactly are the boxes and what are the pointers stored like? I don't think I want to go into this in any more detail. It just shows you maybe that this method is included in all sorts of compression methods. In particular, I should definitely point that out. The zip compression format is pretty much Lempel-Ziv with a few extra twists, or Lempel-Ziv Welch, or variations of that. What all these families have in common is they're more or less the same in what type of redundancy they can pick up. And so that's also why these formats often behave relatively similar. So let's come to the star of our show in this section, the Lempel-Ziv Welch algorithm. It's usually seen as the cleanest version of those, so that's why I'm presenting this one as opposed to another one. But the others, they are similar in spirit. It's a variable to fixed length encoding. We code a variable length substring, but the code words will all have the same size. Think of something like 12 bits as a typical one. If you've played with zip compression, sometimes you can tweak a parameter called the dictionary size. That will pretty much be the number k. Now, how does this work? We maintain a dictionary. Again, that's where this name comes from. It's a list of portions of the text we have seen. Let's call this D, and it has 2 to the k entries. That's simply one entry for each possible code word. If we have k-bit code words, then 2 to the k entries are in the dictionary. We fill the dictionary initially with the single characters. So we assume these are already in the dictionary at the beginning. And then we'll keep adding more things to the dictionary in each step. And what do we add to the dictionary? That's described with something like this picture. So suppose we have encoded our text up to this point. That's the gray part. That's done. And now there's more characters to follow. And we can look ahead at what are the characters that come. Now we find a longest match in our dictionary that starts at this position. So we look through our dictionary and try to find what is the longest thing that I can read from here that I've seen before. And in this example, say that's this substring ban, which occurs before here. I mean, you see the similarity of the picture before. Then that is what you encode. And you encode it by using the entry in the dictionary. So you've seen that before, which means it has a code word assigned in the dictionary. So that code word is your output. But you're not done yet. If you only would do that, you would never ever get to bigger and bigger entries in the dictionary. So the second thing you do is you add a new code word in the dictionary, which consists of the old code word you found plus one more character. So you add this next character, A in this case, and then this combined red and blue part together, that's one new code word that you add to your dictionary to be used in the future. All right, and nitpick in terms of space, you don't really have to copy these strings. Instead, you can say, I'm storing a code word X, that's the one I repeated, and then just a single new character. So these entries in the dictionary, they're all just 2 numbers. Let's see how this works on an example, and I think that will make it clear. I'm assuming here that we're using the standard ASCII alphabet. So we can pre-fill our dictionary with the first few entries are taken just by the ASCII characters. I only show the ones that occur in our text, but of course the others would be there as well. And then we start encoding. At the beginning, it's easy because there's only the single characters in the dictionary. So we find the longest thing we can find here in this yo, you, your, yo-yo is the letter Y, which has code 89. So that's our output. But we're not done. We have to add a new thing to the dictionary at this point. So we take the next character after the Y and add that as a new code word. Okay, then we keep on going. The next character we find is an O. There's nothing longer than the single O in the dictionary, so we encode this. But we add one more thing to the dictionary, which is O and the exclamation mark. Okay? This keeps going for a while like that. You encode a single character because you haven't seen anything bigger than that. And you add to the dictionary what you've encoded plus one more character. It takes a bit before things get interesting. But at this point, the next thing we want to encode starts here. And now we could just take the Y as before, but we actually have YO in the dictionary as well. So we take that because it's the longer match. So we encode the 128. But as before, we add this plus one more character as a new string in the dictionary. And so you see how this builds up longer things in the dictionary to use later. And so if some string occurs many times, you can just reuse the longest version of that. Here we have another one, just a single character, and insert that character plus the next. Here we have another match, so the exclamation mark space, that combination occurred before. So we can add that, and we make a new entry with exclamation mark space Y. And so on. Next one, we find our U again that we used before, so we can make use of the 3-letter code word. And we insert an even longer one. All right. R we haven't seen before, so that's an individual character, and we insert R space. Space Y is something we've seen before, but we haven't seen anything longer, so we take that one and insert a new one, space YO. O we have seen before, but with exclamation mark after it, so the only one is this one, but not OY, so we leave the single O, but add OY now. And one more, so yo we've seen up here, very first one, so encode that and add a new one, and then we're done. Exclamation mark is encoded, then we're done. Okay? So it's fairly straightforward how the encoding works. And you see how it picks up the repeated parts by having longer and longer things in the dictionary. If you put that into pseudocode, you can write it like that. You want to spend a little thought on how to represent the dictionary. If you just have that as a table as in the example, it wouldn't be very efficient. You would have to search through it. But we know a much better way to do it. Once again, the try is what helps. If you keep the code words in the dictionary in a try, you have to change it a little bit because they're prefixes of each other. But the longest match will just consist in you start walking down the try as you read in the text, and as soon as you can't continue, you found the longest match. So that's relatively straightforward and gives you constant time per letter. Then you keep a number, that's the next free code word that you want to assign. And the rest is, as you've seen in the example, following through. So we get the next character from the text. We check if we can move one edge down in the try. If we can, we do that, and we remember in X what the the phrase was that we could read. If we fall out of the try, we found our longest code word in the dictionary, then we append to the coded text the code word for x, and we add the new entry in the dictionary, which is C is always the next character in the text. So XC is added, and we insert K as the value. That's the code word. Then we have to make K1 bigger and reset X to just this single character. And so the code for this is relatively straightforward. We're just plugging in data structures to make it a bit faster.